welcome back, guys. We're going to finish up 9.3, and we're going to look at how an exponential function can be used to model the growth of an investment that earns compound interest. Okay, so this kind of ties back into that graphic that I showed you earlier involving Warren Buffett. I can find it. Yeah, his net worth. Okay, a lot of that was made possible by this idea in finance of compounding. Okay, so let's talk about that just for a minute. So let's imagine that we've got $1,000 and we want to invest it. And we're going to invest it in a savings account or a CD or something like that, or a money market account, and it pays interest. So we're going to make some money with our money. And let's say it pays 10% interest. Okay, this is a bit idealistic. But there's a distinction between an investment that earns simple interest versus what we call compound interest. So simple interest just means you're going to earn 100%, or excuse me, 10% on $1,000 every single year. Okay, so that's $100. So every year you're going to earn $100 in interest. The amount that you earn never increases. But that's different with compound interest. Compound interest actually gets converted back to the principal, or the original amount. Okay, and then that new amount earns interest. So what we have occurring here is it's like we're investing an ever increasing amount, and that's earning interest. Okay, and so that interest payment just keeps getting bigger and bigger and bigger. So that's kind of the idea of compounding. Basically, your interest earns interest, essentially, because your interest becomes part of what you're investing, and then that earns interest. And when you have that sort of thing occurring over a rather relatively lengthy period of time, that can mean some, or translate to some pretty significant financial gains. That's why, you're recommended, or you're urged to start investing in your retirement plan or retirement account as soon as possible. The earlier you are, the better, because that just means you have more time. There's more time over which that money can earn interest. But anyway, we actually have a generic function here that we're going to be using to model that. And we're going to talk about it for a minute. Okay. So you'll notice it doesn't say f of x is equal to, it says a of t. So in the financial world, guys, A represents accumulated value. So what is the accumulated value of an investment after a certain period of time? So instead of x, we're using t because this is a function of time. Remember how in the real world, I told you that a lot of functions are functions of time because so much depends on time. Okay, so I'm going to write this out. And we'll talk about it for a second. Okay. All right. Well, this formula for calculating the amount of money sometime in the future that earns compound interest, it has some parameters here. That's what the P, the APR, and the N represent. These are called parameters. They'll change with the scenario. Okay. Now your independent variable is t, and notice where that is. It's in the exponent's place, so that's why this is an exponential function that we use. So let's talk about this. So A just represents the accumulated value of the investment after some period of time. P represents what we refer to as the principal, or the amount that we're investing, okay, or depositing. Now, if you're on the other end, you would be a borrower, and so the principal in that case would be the amount of money that you're borrowing. Of course, you're the one in that case that ends up having to pay the interest. The APR is an acronym for the annual percentage rate. In other words, this is just represents the interest rate. T is our independent variable. It represents time in years. It doesn't have to be in years, guys, but for this course, it's in years. Okay. And then N represents the number of compounding periods per year. So what does that mean? That means the number of times interest is credited to your account per year. Okay, so typically, unless your account is earning just simple interest, which only grows linearly, compound interest will cause your investment to grow exponentially. Okay. And the reason is because you have that interest compounding throughout the year. And then whatever's left at the end of the year, that's left to then draw interest. Okay. So compounding typically takes place 12 times per year. It's typically monthly. But it doesn't have to be. It could be quarterly, which would mean 4 times a year. It could be semi-annually, which is 2 times per year. That's just the number of times interest is credited to your account. Okay. All right, so let's take a look at an example. We're going to use a function just like this to model the growth of an investment. Try to figure out what's the value of the investment after X or T number of years. Okay. So example 6 here. It says, suppose that $68,000 is invested at 3.5% interest, and it's compounded quarterly. Find the function that models the growth of this investment, and then find the amount of money in the investment after 0, 3, 5, and 10 years. Okay. Just real quickly, there are some things that are paid quarterly. So, for example, if you own stocks in companies, or I think also like bond funds, some bond funds give out dividends on a quarterly basis. As long as you have those dividends used to purchase more shares of whatever it is that you're investing in. But that would be an example. Some things, yeah, anyway, I won't say anything else. But, all right, so what we're going to do is we're going to use that template from above, and I'll recopy it here. We're going to plug in the values for these parameters. This is raised to the n times t power, okay? So we're investing $68,000. 1 plus APR is 3.5%, or in other words, 3.5%, okay? When you put this in your function or in your formula, you want this percentage to be a decimal. So you have to divide it by 100, or in other words, move that decimal to the left 2 places, and it'll become 0.035. Now, 3.5%, that's not a great rate of return on an investment, okay? Over, what's the value of n here? Well, it says that interest is compounded quarterly, okay? So that means 4 times a year, okay? and this will be 4 times t. So this is our function right here. We plugged in the parameters, so we have the specific function that models the growth of an investment in the context of this problem. Okay, and so the rest of this question is just asking us to basically evaluate this function whenever t is equal to 0, 3, 5, and 10. 5 and then 10. Okay. Alright, well, you can do this in your calculator. If you type it in exactly the way it's written. So I'm going to first plug 0 in. So we want to know the value of the investment after 0 years. Alright, so I'm going to type in 68,000. Let me clear this. 68,000 times, in parentheses, all of this, 1 plus 0.035 divided by 4, close those parentheses, okay, and then raise this to the power of 4 times 0, because that's what we're plugging into the function, okay. And when you hit enter, it'll give you the value. Now it's $68,000, okay. But typically I'll ask why. Why is it just $68,000? That's what we deposited. And the answer is because it hasn't had time to grow, right? When t is 0, that represents the point of time in which you deposit the money. Alright, so now we want to see how much we have after 3, 5, and 10 years. So you can do this the same way, but I'll show you a shortcut. You can reuse what you already have in here. If you hit second and then the enter key for entry, it'll re-enter what you just typed in. And then you can simply scroll over and replace that value of t with the new value of t. So 3 in this case. Alright, so here we go. After 3 years, it'll be worth $75,493.83. You're going to need to round to the nearest cent for these. $75,493.83. Okay. Yep. Now I'm going to do it again whenever t is 5 years. Oh, so after 5 years, we've got $80,943 and some change. This is going to round to the nearest cent means the hundredths place, so this is going to round to 11 cents. Okay, and then finally here, guys, I'll do it one more time with the value of 10 for t. There we go. Hit enter, and now it's $96,349.80 if I round it to the nearest cent. Okay. So after 10 years, my investment has increased by close to $30,000. So that's not too bad. But this could have been a lot better if this interest rate was higher. And let's do the same thing. Second entry. Oops. Let's do second entry, and let's change this interest rate to, let's not make it 3.5%. Let's make it something a little more realistic. If you're investing in let's say the S&P 500 over a long period of time, you can expect to get an average return of 8, 9, 10%. Probably more like 8% if you adjust for inflation. Okay, so let's see what it'd be worth at 8% after 10 years. Oh, it's a lot more, isn't it? Let me try this again. Let's do it for, I don't know, 20 years at 8%. Now we're talking 331,000. So this is about $1/3 okay? And let's do one more. Remember, we only started out with 68,000. We kept it invested for 20 years. Now this is a bit unrealistic because when you're saving for retirement, you never typically have a lump sum like this. Typically you just start saving a little, each month. You can invest a little bit each month for years and then decades. It can really add up to a lot of money. That's why somebody like me can end up being a millionaire. It just takes discipline, really. And let's change this to 40 years. So this might be a person's working lifetime. Let's see how much it is. Wow, now it's $1.6 million, okay, after 40 years. So that's why you want to start investing for retirement as early as you can. I didn't start as early as I could, guys. I wish that I had. I did, however, start a lot earlier than a lot of people. If you start too late, you'll never have anything. Your investments will never have time to grow to the point where you can actually retire. And I know people like that, which means you're going to be relegated to working for the rest of your life. So, I know when you're young, you know rationally that you're going to die, but it's not real, it's not tangible, it's not something you're really thinking about, right? I can remember putting myself in my 20-year-old shoes. That was the last thing that I was worried about when I was 20 years old, was investing for retirement. But if I could have just made a few sacrifices every month, if I could have just taken like 5% of whatever I made and invested it, or even better, 10%, I'd be in much better shape than I am now. Okay, so the moral of the story is try to plan for retirement. Okay, don't think that you're going to be able to depend on Social Security, or so it may not even be around. All right, well, this example, I think, captures the sequence or the reasoning that you're going to need to do these homework problems. Last thing I want to mention here, guys, is this special number e. So, first of all, what is it? Well, it's an irrational number, so it's similar to the number pi, okay? But it's actually used in exponential equations. This is one way. It's used in exponential functions to model processes that grow continuously. So, for example, if you had an investment, instead of, what if it wasn't compounded quarterly or monthly or even daily, what if it was compounded continuously? Then that's where this number kind of makes an appearance. Okay, this number is actually, the definition of it comes from calculus, but we're not going to get into all that. We will see this again at the end of the course when we're trying to model the growth of populations or the decay of radioisotopes as a function of time, and we use this number. We can view or we can model those processes as continuous processes. Alright, so this number is approximately equal to this value here. Notice, this just means it goes on forever, and there is no pattern by which these digits repeat. Okay. All we're concerned with, at least now, is just how can we perform a few computations using this number e? Well, there's a key in your calculator, okay? So I'll do some of these to show you. There's two ways. There's one right here above the division function. So if you hit that, and then you raise e to the third power and hit enter, you'll get a decimal approximation. And you'll typically want to round these to, I think maybe it's 4 decimal places. Okay. Or another way to access e is by hitting second, and then this key right here that has that e to the x above it. And it'll put the cursor in the exponent's place, so then you can type in whatever you want that exponent to be. So negative 0.03 or 0.023. Hit enter, and we get, oh, I'll put an extra 0 in there. I was wondering why this wasn't matching. Delete that 0. There we go. Okay. And then e to the 0 is just 1, because remember, anything to the power of 0 is 1. Alright, but that's all you'll be doing in this section, just a couple simple calculations using e. And those answers will be approximations, remember, so you'll be rounding those. Alright. One last thing I would sort of like to do is let's graph this function in Desmos here real quick, just for fun. 68,000 1 plus 0.035 over 4. Now again, remember I said that's not a great interest rate. Raise this to the 4 t power. Desmos will understand this is a multiplication up here. And you may be wondering, well, we don't see anything. Well, what I want to do is I want to restrict my y-axis. I only want to see part of the y-axis. Y, let's say greater, whoops, greater than or equal to, let's say 68,000. Okay. I'm getting an error.
One thing is they have to have an email.
Well, Alright, sorry about that, guys. I couldn't get it to. I couldn't manipulate the viewing window in Desmos such that we could really see this. So what I did is I graphed it in my calculator, where I'll put the function in my calculator here. And I'm going to adjust the window. Because the values from this function are so large, they start at 68,000. I need my y minimum. I'm going to set it at, I don't know, 60,000. And I'm going to let my y maximum, we'll say, let it be 3 million. Well, that's probably way too large. But we'll let it be a million. There we go. And then of the x-axis, I want this to start at 0, and I want it to go to, say, 50. So for 50 years, okay. Now I'll graph it. There we go. So when I manipulate my window there, you can see this is an exponential curve here, right? This is over a period of 50 years, and so if you come over here to trace, it'll put your cursor on your function, and you can see the coordinates for where that cursor is. So when x is 25, it means after 25 years, this is how much you would have, $162,500. Okay, but as I go to the right, or as the years increase, you can see the value in my account is increasing all the way. Well, here we're past 40 years. I made this go to a maximum of 50 years for X. So at 50 years, you would have almost $400,000 with $68,000. Okay, but again, this interest rate is really small. But what I really was focusing on was trying to show you this exponential curve, and also pointing out that the steepness of these curves is not going to be like that we saw earlier. Okay, and the reason is because the base, here we go, well, the base of these functions, this piece right here, ends up being a little bit over 1. Okay, so it's not like a base of 3 or a base of 5. It's always 1 point something. So that's why these functions aren't as steep. But anyway, and my video froze. Alright guys, well that's it for this one. And next section we're going to look at 9.4 on logarithmic functions. So those functions do just the opposite of these exponential functions. Instead of plugging numbers into an exponent, you plug numbers into a logarithm, and the logarithm tells you what the exponent was. So because they're inverse functions, but we'll talk about that in the next video.